Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we consider third topic. It is known as total differential equations. Let us consider the definition of total differential equations. A differential equation of the type p dx plus q dy plus r dz equal to 0 where p, q, r are functions of x, y and z is called total differential equation. That means equation of the type p dx plus q dy plus r dz equal to 0 where p, q, r are functions of x, y and z is known as total differential equation. Now we consider the condition of integrability of this total differential equation p dx plus q dy plus r dz equal to 0. Let the total difference in this condition of integrability, we write the total differential equation p dx plus q dy plus r dz equal to 0, denote it as equation number 1. If u equal to c, where u is function of x, y, z, is integral of equation 1, that is solution of equation 1, then we must have du equal to dy by dy x dx plus dy by dy y dy plus dy by dy z dz equal to 0. Denote this as number 2. Comparing 1 and 2, we get dy by dy x upon p equal to dy by dy y upon q equal to dy by dy z upon r equal to mu c, where mu is function of x, y and z. Dy by dy x equal to, from this we get dy by dy x equal to mu into p, dy by dy y equal to mu into q, and dy by dy z equal to mu into r. Denote this as number 3. Now we differentiating first two equations of 3 with respect to y and x respectively. That means we differentiate this with respect to y and we differentiate this equation with respect to x respectively. We get dy 2u by dy y dy x equal to mu into dy p by dy y plus p into dy mu by dy y. That means we differentiate this both sides with respect to y, and we differentiate this both sides with respect to x. So we get dy 2u by dy x dy y equal to mu into dy q by dy x plus q into dy mu by dy x. But we know that in general dy 2u by dy y dy x equal to dy 2u by dy x dy y. Hence we get both the RHS sides must be equal. Hence mu into dy p by dy y plus p into dy mu by dy y equal to mu into dy q by dy x plus q into dy mu by dy x. Hence, taking mu common, we get mu into bracket dy p by dy y minus dy q by dy x bracket complete equal to q into dy mu by dy x minus p into dy mu by dy y. Denote this equation as equation number 4. Thus, by considering first two parts, we get this equation 4. Similarly, we can obtain mu into bracket dy q by dy z minus dy r by dy y equal to r dy mu by dy y minus q dy mu by dy z, which is number 5 equation, and mu into bracket dy r by dy z minus dy p by dy z bracket complete equal to p into dy mu by dy z minus r into dy mu by dy z, which is number 6. By considering second and third part, that means we get these equations. Here we get this equation number 4. We get this equation number 4 by considering first two parts and multiplying this equation with respect to y and multiplying this second with respect to x. Similarly, by considering these two, second and third, and we differentiate this with respect to z, and we differentiate this with respect to y respectively. So we get this equation number 5. And by considering this last term, that is delta u by delta z equal to mu into r, and delta mu by delta x, delta u by delta x equal to mu into p, that is 3 and 1, third and first part, and differentiating this with respect to x and this with respect to z, we get, in similar process, we get this equation number 6. Now we multiply these equations 4, 5 and 6 by r, p and q respectively, and adding the corresponding sides, we get mu into bracket p into bracket delta q by delta z minus delta r by delta y bracket complete plus q into bracket delta r by delta x minus delta p by delta z bracket complete plus r into bracket delta p by delta y minus delta q by delta x bracket complete and whole bracket complete equal to 0. But mu cannot be 0. Hence p into bracket delta q by delta z minus delta r by delta y bracket complete plus q into bracket delta r by delta x minus delta p by delta z bracket complete plus r into bracket delta p by delta y minus delta q by delta y bracket complete equal to 0, since mu is not equal to 0. This is the condition of integrability for the total differential equation. But this condition can be put, equation number 7, which is denoted by equation number 7, can be put in the form determinant of PQR delta by delta x delta by delta y delta by delta z equal to 0. That means the condition of integrability for total differential equation is dash dash, that is determinant equal to 0, or p into bracket delta q by delta z minus delta r by delta y plus q into bracket delta r by delta x minus delta p by delta z plus r into bracket delta p by delta y minus delta q by delta x equal to 0. This is condition of integrability for total differential equation. But to remember this condition of integrability, it can be remembered in simple way by taking determinant equal to 0, that is PQR delta y delta x delta y delta y delta y delta z equal to 0. After expanding this determinant, we get this condition of integrability. So we denote this, and this is the condition of integrability for total differential equation. Thus, this is the necessary condition for the integrability of the equation, total differential equation p dx plus q dy plus r dz equal to 0. It can be proved that the condition 7 is also sufficient condition. Now we consider method of solving the integrability equations. Here, consider first method, treating one variable as constant. That means if the equation condition of integrability is satisfied, then we put one of the variable in this method, we put one of the variable as constant. That means in this method, given total differential equation is p dx plus q dy plus r dz equal to 0. Let the condition of integrability be satisfied. Now we take one of the variables, say z is constant, so that dz equal to 0. If dz equal to 0, then this 1 becomes p dx plus q dy equal to 0. We denote this as equation number 2, and which can be easily solved. Let the solution be u equal to c. Now replace the arbitrary constant c by an arbitrary function, say z, arbitrary function of z, say phi of z. Hence, u equal to phi of z is the solution of p dx plus q dy equal to 0. Now we differentiate this u equal to phi of z with respect to x comma y comma z and compare the result with the given equation to find u equal to phi of z. That means here we first consider total differential equation and we check whether the condition of integrability, that means this determinant equal to 0 or not. If this determinant equal to 0, that means condition of integrability is satisfied. Then we take one of the variable, say z is constant. So we get dz equal to 0. So that total differential equation becomes p dx plus q dy equal to 0, which is easily integrable. Then we get one solution of the type u equal to c. Then replace this c by arbitrary function of z, that is phi of z, that is u equal to phi of z, be the solution of this equation p dx plus q dy equal to 0. And now we differentiate the solution with respect to x comma y comma z and compare the resulting equation with given equation to find u equal to phi of z. And second method is method of inspection. Here, if the integrability condition is satisfied, that means we have to check the condition of integrability. First write given equation in the solution and check whether the condition of integrability, that means determinant pqr deba y deba x deba y deba y deba y deba z equal to 0 or not. If the condition of integrability is satisfied, that means determinant equal to 0, then sometimes by rearranging the terms, the given equation becomes exact. Hence, by direct integration, we can obtain its solution. And third method is method of substitution. In this method, the given integrable equation p dx plus q dy plus r dz equal to 0 is such that p, q, r are homogeneous functions. That means given function is homogeneous, that means degree of every term is same. Then we put x equal to uz and y equal to vz and solve in same manner. Hence dx equal to z du plus u dz and dy equal to z dv plus v dz. We can solve these equations. Now we consider geometrical interpretation of this total differential equation p dx plus q dy plus r dz equal to 0. We consider this total differential equation p dx plus q dy plus r dz equal to 0. Denote this as number 1. Let u equal to c, where u is function of x comma y comma z, be the integral of this equation 1, that is solution of this equation 1. Hence we get w by dw x dx plus w by dw y dy plus w by dw z dz equal to 0. Denote this as equation number 2. Comparing 1 and 2, we get w by dw x upon p equal to w by dw y upon q equal to w by dw z upon r. This is number 3. But w by dw x, w by dw y, w by dw z are proportional to direction cosines of normal to the surface u of xyz equal to c at point p x comma y comma z on it. Hence 1, that means total differential equation p dx plus q dy plus r dz equal to 0 represents a single infinite system of surfaces such that direction cosines of normal at any point p into bracket x comma y comma z bracket complete on the surface are proportional to the values of p comma q comma r at that point. That means direction cosines of normal at any point p on the surface are proportional to p comma q comma r At that point, this is the geometrical interpretation of total differential equation P dx plus Q dy plus R dz equal to 0. Thank you.